In a nuclear reactor, nuclear fission produces heat in the generator's core. This heat causes steam to raise in the generator, which forces the movement of turbines. These turbines power generators, producing energy. After powering the turbine, the steam is condensed back into a liquid, so it can re-enter the generator to be heated again, and the cyclic process continues. Because of the exorbitant amount of heat produced from nuclear fission, the heat also causes a coolant to be moved throughout the reactor, which cools it. Because of the dangers associated with nuclear reactors, such as overheating, radioactivity, and meltdown, they are generally kept in some kind of protective concrete dome-shaped structure that is able to handle internal and external situations that may harm the reactor or the areas surrounding it. Also, nuclear generators are normally placed near a body of water to help with cool down. However, one risk of that is to be cautious of the fish and nearby aquatic creatures living in that area. There are some devices that are integral for a nuclear reactor being in safe working condition. The moderator is located in the reactor's core and slows the speed of fast neutrons so that they become thermal neutrons that are capable of fission. Control rods are also in the core and are made of materials that are capable of controlling the rate of fission of the nuclear material without undergoing fission itself. Finally, a heat exchanger keeps the two liquids separated by a material such that the heat can be transferred between them without them ever touching or mixing. Though there are many moving parts to the reactor, the transformation of energy within it is quite simple. The process starts with nuclear energy. As fission occurs, all of the nuclear energy is converted into thermal energy due to the heat being produced from fissioning. As the steam produced is run through the turbine, 75% of the energy is lost. The remaining 25% of the energy is converted into kinetic energy as the turbines spin to provide energy to the generators. This energy is finally delivered in the form of electricity to the customers. This model can be seen in our Sankey diagram in the infographic. To put into perspective just how much energy this is, uranium-238, which makes up 99.3% of natural occurring uranium, produces 79,390,000 millijoules per kilogram of energy. Uranium-235, which makes up the other 0.7% of natural occurring uranium, produces 80,620,000 millijoules per kilograms of energy. Because of how much power can be produced from just one nuclear power plant, as of July 2015, 30 countries are operating on 438 nuclear reactors. In total, nuclear power plants provide 10.9% of the world's electricity production in 2012. Possibly most impressively, in 2014, 13 countries relied on nuclear energy to supply at least 1/4 of their total energy. As you can see, nuclear energy is vital in the world's production. In recognizing that so much of the world does not rely so heavily on nuclear energy, it's important to understand the advantages and disadvantages of nuclear reactors. Advantages include the fact that nuclear reactors only account for a small contribution to global warming because of the relatively low amount of carbon dioxide produced from a plant. The fact that the technology to make such a plant is readily available and does not require further technological innovation as another form of energy might be another example of an advantage. The last advantage is the high amount of electrical energy that can be produced from one single plant, as we heard the numbers before. Disadvantages include the radioactive material that is created from nuclear energy is extremely dangerous and takes thousands of years to decompose. The fact that it is technologically impossible to build a plant with 100% security, meaning that failures will always be possible, and therefore that the more nuclear power plants there are, the higher the possibility of catastrophic failures, as we see with some of the famous histories, Chernobyl, and other examples. And finally, the fact that uranium is a scarce resource that is being consumed very quickly with nuclear plants. So it's a great source of power and energy, however, it's hard to find and you can really screw it up. Important safety issues and risks to note are that a failure or meltdown can release large amounts of radiation that is extremely harmful to the environment and has been scientifically proven to cause cancer. Additionally, nuclear power plants tend to be a prime target for sabotage or terrorist attacks because of the explosive power within one, as well as its being home to materials that can be easily converted into nuclear weapons. This was seen in the recent attacks in Belgium, where terrorists were tried to attack the nuclear power plants in Brussels. There are also various problems associated with producing nuclear power using nuclear fission. With today's technology, the energy output from nuclear fission is less than the energy's input that is needed to start the reaction. Therefore, it is not a good resource for producing energy just now. But in theory, if we can perfect the way it's in controlling and activating the reaction, nuclear fission would not require expensive mining like nuclear fission. And also, there are relatively less nuclear waste. To have the reaction take place and be sustained, the environment that the reaction takes place must be kept at a consistent temperature around 100,000 degrees Celsius, which is extremely hot, and this would need a lot of resources to just maintain the temperature that high. Also, a magnetic field strong enough to control the reaction must be created for the reaction to occur safety. Once again, a lot of safety issues that take place. So let's look at an example that we can use to help figure out nuclear energy. So our first problem is if an individual uses electrical energy at an average rate of 1 kilowatt, what is their annual energy consumption? So the key with this problem is to use the factor label method, converting 1 kilowatt to joules. So as you can see, they go from joules to seconds, seconds to minutes, minutes to hours, hours to days, and days to year. So moving on, the next question is what mass of U-235 atoms has to undergo fission to provide the energy needed for a year, consume 100% efficiency. So as we learned before, it's very difficult to gain 100% efficiency. So what we did here is we times 24,000 kilowatts per hour over 1 kilogram U-235, which is something that we looked up, and we found out that's how much kilowatt per hour is produced from 1 kilogram, and we converted that to grams. And then from there, we times it by the joules of work used per 1 kilowatt hour, and we got our total, which we divide by an efficiency of 3.2 times 10 to the 10th joules per year, and we ultimately got 0.4 grams per year. In conclusion, nuclear power efficiency is a very reliable process. However, it can be difficult to execute. It works well for getting good that energy production, but can be risky with the environment, and uranium is a very difficult resource to obtain.